All right, I'm just going to repeat these things really quickly for the people who are absent today. In this case, we found the probability of A and we found the probability of B, and this is not in the notes packet. We just did it instead of the other warm-up. And then we found the probability of A or B was 6 out of 10 or 0.6. And we were surprised that it's not the same as adding these. What we realized is that if I add the 3 in A to the 5 in B, I end up counting that middle part twice. And so this will not equal the sum of these two. Which brought us to the addition law of probability, which is the probability of A or B is probability of A plus probability of B, but you have to subtract out that middle part because you counted it twice. So we're now about to use this formula. Probability A or B equals probability of A plus probability of B minus the probability of A and B. And I'm substituting in. Probability of A is 0.6. Probability of A or B is 0.7. And probability of A and B is 0.3. All right, so we can use that formula to find the probability of B. So these two combine to make 0.3. And then I can subtract that from both sides to get 0.4 is the probability of B. Yes, of course. Okay, what questions did you have on that? You can also tell me when I need to move that higher, okay? I know sometimes it's hard when it's lower. I can read it to you too. Sometimes it's just not that clear. All right. When you're ready, you can turn the page. All right, 30 students were given a history test. 7 students scored an A and 11 students scored a B. A student is randomly selected. Let A be the event that the student scored an A, and let B be the event the student scored a B. Are A and B mutually exclusive? Meaning, is it not possible to have both an A and a B on the same test?
Yes.
Yeah. So they are mutually exclusive, which means that there is no overlap. No students had both an A and a B on the same test. All right, so the probability of A was 11 out of, did it say 30? Yeah, 30. And then the probability of, no, I didn't get that right. You guys have to tell me when I don't get something right. It's 7, thank you. The B is 11 out of 30. The probability of getting a and a B. Olivia says 0. Anybody agree? Good. Yep. 0 out of 30 students got an A and a B, which is 0. So because these are mutually exclusive, you can just add the probability of A and the probability of B to find the probability of A or B. But if you wanted to, you could still subtract the probability of A and B, because that's not going to change anything, right? So you can leave that off, or you can put it there. Same answer. We got 18 out of 30, which we should simplify.
Yes,
Oh,
yeah.
sorry. What is it?
3/5.
3/5? Good. Yeah. I like fractions. All right, so that wasn't too hard. All right, 2 events are independent if the occurrence of one event does not affect the occurrence of another event. Okay? Independent. All right, if A and B are independent events, then the probability of A and B happening is the probability of A times the probability of B. So if the probability that I'm on time today, well, not today because it already happened, tomorrow, is 50%, 0.5, and the probability I'm on time the next day is 50%, 0.5, the probability that I'm going to be on time both Thursday and Friday is 0.5 times 0.5, which is 0.25, okay? So when you have two independent events, then to find the probability of them both happening, you just multiply their probabilities. And you can do that too if there's 3 events or however many events there are, okay? All right, let's look at number 3. A coin is tossed and a die is rolled simultaneously. Determine the probability of getting a head and a 3 without using a grid. So what's the probability of a head? 50% or 0.5. So probability of a head, you could say 1/2 or 0.5. Probability of getting a 3 is 1 out of what? 1 out of 6. Good. And that decimal is not nice. It doesn't end. So let's use the fractions. So the probability of a head and a 3 is 1/2. Oops, that's not 1/2. 1/2 times 1/6. And it gives you the 1/12. All right, so odds are really not in your favor there, that you're going to get both a head and a 3. Only 1 in 12 chance. Liam rolls a 6-sided die twice. Determine the probability that exactly 1/4 is rolled. So that's tricky because it means a 4 and a not 4. You can actually do it this way. The notes have a tree diagram on them. I don't know, let's see. So either the first one's 4 and the second one's not 4, right? 4, not 4. Or the first one's not 4 and the second one's 4. So either we're going to have a 4 and a not 4, or we're going to have a not 4 and a 4. So the probability of a 4 is 1 in 6. What's the probability of a not 4? 5 and 6, yeah. So the probability of both of those things happening is going to be 5/36. And then if I switch up the order, it just changes this. This is 5, 6, and this is 1, 6. And so then this is going to be another 5/36. So there's a 5/36 chance that we get this, and there's a 5/36 chance that we get this. So we're going to add those together. So when there's 2 different ways you could win the game, then you just add those 2 together to find the probability that you're going to win. And of course you simplify. Okay. We can also use a tree diagram to describe these independent events. I see a couple people writing, and then I'll go look at the next one, but go ahead and read about Carl. All right. Carl's not having much luck lately. His car will only start 80% of the time, which is what decimal? 0.8. So there's a 0.8 chance his car is going to start. And his motorbike only 60% of the time, so 0.6. Independently of one another. So like the motorcycle doesn't wake up in the morning and say, oh, the car didn't start, so I also won't start, right? So they are independent. So what we're going to do is we're going to make a tree diagram that starts with a car. C means the car starts, and not C means the car does not start. So remember that little line means not? And then after that happens, the motorcycle may or may not start. Start, not start. Start, not start. So the probability of the car starting is 0.8. And then that means the probability of the car not starting is what? 0.2, good. So 80% chance it starts, 20% chance it doesn't. What will I put on this line for M? 0.6, good. The motorcycle, 0.6 chance of starting, and then not starting, 0.4. And those numbers are repeated down here. 0.6 and 0.4. It says use the tree diagram to determine the chance on the next attempt both will start. So you're going to follow the car starting and the motorcycle starting, and you multiply them. 0.8 times 0.6. All right, so a little bit less than half. A little less than 50% chance that they're going to both start. All right, and then try to figure out the next one, the probability that Carl will use only his car. Oh, can only use his car, because that's when it starts. And then compare your answer with your neighbor. Yes. On this hallway, yeah. All right. So probability he can use his car is 0.8, right? But then we have to say not his motorcycle. And I got 0.32. Oops. Does that make sense? All right, so those are independent events where one doesn't change the other. A lot of times when they talk about dependent events in a very introductory probability course, they talk about choosing things from a bag. You could also think about choosing students, right? So if Mr. Seward comes here and he says, I'm going to pick my 3 favorite students, right? And he picks Jessica. And then you think, oh, it should have been me, right? But all of a sudden, you have a better chance because I don't know how many there are here today, but let's say there's 25 of us, right? So you had a 1 in 25 chance, but then Jessica leaves because she's already one of the favorite students, and now you have a 1 in 24 chance, right? And then another student leaves, and then you have a 1 in 23 chance, and then hopefully you're picked because that's it. He's just picking 3. Okay? All right. So dependent events, the odds change each time the experiment happens. So here the hat has 5 red and 3 blue tickets. And 1 ticket is randomly chosen, and its color is noted and then put aside, so it's not put back in the hat. So the probability that the first ticket is red is, there were 5 red tickets, right, out of 8. But then the probability of the second ticket being red, so I think we're supposed to write that here, which is weird. The first one being red was 5 out of 8. But then after you take out that red ticket, the probability that the second is red is 4 out of 7 because there are 4 reds remaining out of 7 tickets altogether. And then if the first ticket was blue, there were 3 blue tickets out of 8. But then that the second is red, notice that there's still 5 reds, but we're taking out of 7 tickets altogether. So it says the probability of the second ticket being red depends on what color the first was. We therefore have dependent events. And they are dependent if the occurrence of one of the events does affect the occurrence of the other events. And here's another formula. Can you guys find if this one's in your formula book? I know a few of you took your formula book out. The way that they write the probability of B given that A has occurred is like this. Probability of B given A. It's like a straight line here. People always think it's like a dividing, and you do end up dividing, but that's not what it is. It just means the word given. So the word given is this line right here. In general, when an experiment involves sampling without replacement, then we have dependent events. So that means when you take your favorite student out of the room, That's dependent because it changes your odds, right? But say that you every day you pick a different favorite student, but it could be the same person and they don't leave the room, right? Every day you have the same odds, and so we would have independent events. So if it is with replacement, then we have independent events. So it says not all scenarios we study involve samplings. They may involve dependent events. For example, the event Pahal walks to school today is dependent on the event it will rain today. So how you get to school probably is dependent on whether it's going to rain or not. You good? Okay. Okay. All right. We have 4 red and 2 yellow tickets. And they are chosen without replacement. So once you take a ticket out, you don't put it back. Find the probability that both are red. So the first one and then the second one. For the first one, there are 4 red out of how many altogether? 6, right? All right, then you take a red ticket out. You got a red ticket, you take it out. How many red tickets are left? 3 out of how many? Yes. So this is what we multiply to find the probability that they are both red. Okay, go ahead and find the probability that the first is red and the second is yellow. Okay. All right, first one red is same, right? 4 out of 6? Does it start the same? Okay, second is yellow, so I took a red one first. Do I still have 2 yellows? Out of how many altogether? Out of 5, good. Because I took a red ticket out, I still had 2 yellows, but 5 tickets altogether. All right, for number 7, let's make a quick list of primes, and then I think you can do that one. And then we'll talk about 8 together. So for number 7, prime numbers can only be divided by 1 in themselves. This definition of prime does not include 1 as a prime, so it includes 2, 3, 5, 7, 11, 13, 17, and 19. All right, so try problem 7 with that understanding of primes. Okay, probability of the first one being prime is 8 out of how many? 20, thank you. But then we got rid of one of our primes, and so the next one is 7 out of? Yeah, 7 out of 19, and then the last one? 6 out of 18. All right, let's put that in the calculator, and we'll do both a 3 sig fig answer, and we'll do a reduced fraction. Ask me that when we're closer to our test day. I'm good with both of those, but strangely they don't use percents, even though percents like seem to make more sense to us. All right, so we get that, and then we can also do math fraction. All right. 14 over 285, which is approximately 0.0491. All right, you guys ready to do the petunias? 2 boxes, each contain 6 petunia plants, and so we can draw a picture of that. There's box A, and there's box B, and we're gonna draw the 6 petunia plants. It says box A contains 2 plants with purple flowers and 4 plants with white flowers. And box B has 5 plants with purple flowers and 1 plant with white flowers. Wait, did I do that wrong backwards? 5 plants with purple flowers, yes. Just 1 with white flowers. That's a P. It says a box is selected by tossing a coin, and then 1 plant is removed at random from it. So they randomly select the box, and then they randomly select the plant. So this is just what it said. It said box A has 2 plants with purple and 4 with white, and box B has 5 plants with purple and 1 with white. So find the probability that the plant was taken from box A and has white flowers. So what's the probability that we get box A? 1 out of 2, which is 50%. Good. So 1 out of 2 is the probability of box A. And then, yes, so once we have box A, then we're going to say 4 out of 6. We don't consider all the flowers because we already know that it's box A. So 4 out of 6. Okay, I want you to try B. It's a bit of a challenge, but you can do it. Where is my cursor? All right, guys. So a lot of you guys told me 7 out of 12, and you got to your answer because looking at this holistically, there are 7 purple flowers out of 12 flowers altogether, right? It is the right answer, but your reasoning is maybe not completely sophisticated because you want to consider the chances that you got box A or box B. So your answer 7 out of 12 works because we have an equal chance of getting each box. But if the chances were different, if for example like you rolled a die and you landed on 1 and you get box A, and if you land on 2, 3, 4, 5, 6, you get box B, then you wouldn't have equal chances of both boxes and it wouldn't be 7 out of 12. So we're going to do a slightly more sophisticated answer method that will work for these harder situations, okay? So the probability that you get box A and it's purple is going to be the 1/2 probability of getting box A, and then the 2/6 probability of getting purple, which is 2 out of 12 or 1/6. The probability of getting box B and purple, purple, is 1/2 times 5 out of 6. 5 out of 12. And then you put those 2 probabilities together by adding them. So the probability of purple is going to be the 2/12 probability of getting A in purple plus the 5/12 probability of getting B in purple. And I know some of you got 7 out of 12 right away and you're happy with that answer, but I'm trying to tell you that this more complicated solution method will be helpful when you don't have equal chance of getting both boxes. So you found the probability of getting purple when you have box A, probability of purple when you have box B, and then you add those together to find the total probability of purple. Yeah. So first you have to have the probability that you chose box A, and that's the 1/2, because I think it said you flip a coin. Yeah, it was a good question. All right, you guys ready to turn the page? Okay. All right. So they always have like a bag with tickets or a bag with marbles or something like that, okay? So this bag has 10 balls, and 6 are black, and 4 are white, and 3 are drawn without replacement, so they're taken out each time. You want to find the probability that exactly 1 is black, okay? Exactly 1. So you have to think about the situation. The situation could be black, white, white, right? It could be white, black, white, or the last one, it could be what? White, black, white. Did we say that one yet? Okay, let's write it down and we'll have it. So it would be the probability that you have black and then white and then white, plus the probability that you have white and then black and then white, plus the probability that you have white and then black. All right, so each of these is going to be a conditional probability event. So you have to figure out this probability and then add it to this probability and then add it to this probability. So take a moment to do that. Work with your group. All right, so it is a lot of steps, but it's still the same method. There were 6 that were black out of 10, and then there were no longer 10 left. There were only 9 left. 4 of them were white. And then after you take a white one out, then 3 of them are white out of 8 altogether. Okay? So you can see you get all of these. Each of these equals 1/10 when they're simplified. So your odds altogether are 3 out of 10. All right, guys, we're getting there. Let's quiet down and let's look at the conditional probability part. Okay. All right, so the Venn diagram shows a number of students in class who study Italian and French, and that's a lot of students studying Italian and French. Suppose a student is randomly selected from the class and it's found that the student studies French. We can determine this probability that the student also studies Italian, and this is called a conditional probability. Conditional probability. Because it's the probability of I occurring on the condition that F has occurred. So you could say that this line down here means on the condition, but that's a lot. You can also just say given. Okay, so it's just the number of students who study both Italian and French divided by the number of students who study French. This is the notation. That line means the word given or on the occasion of. And this is called the conditional probability formula. And it should be in your packet, but you should definitely verify that. All right. I do think that we have a problem that's conditional probability, but it's not this one. This problem is drawing a Venn diagram. I do know that the number out here is 0.3. I'm actually going to show you 2 ways to solve this. One will be in the video because I'll be explaining it right now. The other's in the PDF. You can decide which way you prefer. But it just occurred to me that we could actually apply our formula from the first page here, right? So this formula from the first page, I'm just going to copy it here. I'll use C and D. So the probability of C or D is equal to the probability of C plus the probability of D minus the probability of C and D. This is the number we don't know. We don't know the probability of C and D. We don't know what number to put in the middle here. But we actually do know C or D. What's the probability of C or D, looking at what we filled in into the Venn diagram? Point 3 is out here. How much would be in C or D? 0.7, yeah. So C or D, remember, it could be C or D or both, right? So probability of C or D is 0.7. Probability that they own a cat is 0.25. Probability that they own a dog is 0.55. And this is what we don't know. All right, so that gives me 0.8, I think. So 0.7 equals 0.8 minus the probability of cat and dog. And so negative 0.1 equals negative probability cat and dog. So 0.1 is the probability of cat and dog. Once we know that this is 0.1 in the middle, we can figure out everything else, right? If that's 0.1 and probability of cat is 0.25, what number is going to go to the left of it? %25 is 0.25, right? This is already 0.1, so if I put a 0.15 here, that makes a total of 0.25. How about the dog? The dog is 0.55. 0.45, good. Now, as a check, make sure it all adds up to 1. Remember, 1 is 100%, so make sure all your numbers add up to 1. So I got 0.15, plus this is 0.25, plus this is 0.7, plus this is 1. We got it. Okay? All right. Make sure you got that down, because I am going to show you this other method. You don't have to write down both methods. This one's on the PDF that is on your unit overview. I'm just going to show it to you real quick. Okay. For this one, we don't know how much is in the overlap, so we put in X for what we don't know. We don't know, so we put in X there. For the cats, it would be 0.25 minus X, and for the dogs, it would be 0.55 minus X. Because we're going to subtract out that middle part to find out how many is just cats and just dogs. We did know that this is 0.3, that was given. And then they add up the 0.25 minus X plus the X in the middle plus the 0.55 minus X plus the 0.3. We know that makes 100%, which is 1. And so then they solved it this way. So they solved it like a little algebraically. If, for example, you were like lost without your formula book and you didn't have that formula, you could use that method too. You really don't have to rush to write down that method. It's available for you in Schoology. So I'd rather just move on to the next page. All right, on back. Almost done with these notes. We're going to use that Venn diagram now to find the probability that they own a cat given that they own a dog. They own a cat given that they own a dog. Probability that they own a cat given that they own a dog is the probability of both happening, cat and dog, over the probability of dog. I just copied that formula from the previous page. I changed A and B to C and D. That's all. All right, so for cat and dog, I think we had 0.1, right? There was 0.1 in the middle. And then probability of dog they gave us, it was 0.55. So we're gonna divide that. And I'll give you just a 3 sig fig answer. And now I want you to try 2. I'm just gonna write down the notation for it. Probability that they do not own a dog, given that they own a cat. Okay, you can use the same formula, just change it up a little bit. All right, guys. The probability that they don't have a dog and they have a cat. The probability that they don't have a dog and they have a cat. We have to look back at the picture. And we're looking at these people here, here who have a cat and they don't have a dog. So that would be where you got your 0.15 from. All right, so on your Venn diagram, on the left side, there were 0.15, 15% of the people had a cat and not a dog. Cat and not dog. Over all of the people who have a cat, which is 25%, and you get the 0.6.
Wait.
All right. Any questions before I move on? The top shelf in the cupboard contains 3 cans of pumpkin soup and 2 cans of chicken soup, and the bottom shelf has 4 cans of pumpkin soup and 1 can of chicken soup. Lucas is twice as likely to take a can from the bottom shelf as he is from the top shelf. So the first thing he does is he chooses a shelf. All right, so you got top and you got bottom. If he is twice as likely to choose from the bottom shelf, what are the odds he's going to choose from the bottom shelf? What? All right, I heard 2 answers of 0.66 over there. So it could be 0.66 and then the other one would be what? 0.33. So this one would round to 0.67. This would be the 2/3. So 2/3 chance of the bottom shelf, 1/3 chance of the top shelf. That's twice as big as that, and it adds up to 1, which you have to add up to 1. All right, and then once he chooses a shelf, for some reason he's randomly choosing his soup. So he's got pumpkin soup and chicken soup. But remember, the shelves are different. So on the top shelf, where are we? The top shelf, 3 pumpkin and 2 chicken. So 3 out of 5 and 2 out of 5. And then the bottom shelf is 4 pumpkin and 1 chicken. So 4 out of 5 and 1 out of 5. All right, suppose that Lucas takes 1 can of soup without looking at the label. Find the probability that it is chicken soup. Now remember, he's not just choosing randomly from the cupboard. He is first choosing from either the top or the bottom, and then he's choosing his soup. So take a moment and try to do that one. All right, you guys are doing a great job working together. Let's just make sure you got the first one right there. So probability of the top shelf and chicken soup was 1/3 times 2/5. And then probability of bottom shelf and chicken soup was 2/3 times 1/5. And you got 2/15 and 2/15, so you got 4/15. You good with that? I know a lot of you already started the last one, so let's look at it together. It's the probability it was taken from the top shelf given that it's chicken. So top shelf given chicken, you have top and chicken over probability of chicken. So top and chicken, 2/15, probability of chicken, 4/15, which simplifies to 1/2.